Hello everyone, I'm Dmitry Khovratovich from ABDK Consulting and in parallel also from Ethereum Foundation. So some of you may know me as an auditor, some as a cryptographer. And today I'd like to talk a little bit about security of DeFi and internal applications in the world of zero knowledge. And well, the talk is pretty short, but I would like to introduce you to some really nice bugs that you can see there so that you can get some understanding what are the real problems of when you coding your application in zero knowledge. So you may be familiar with zero knowledge not only in the context of proofs, but also in the context of rollups. And you may know that a typical scenario in Ethereum is, of course, you just submit a transaction, then it's executed on all nodes, and then the storage is updated with the results of the transaction, well, if it's executed correctly. And in the ZK rollup scenario, it's a little bit different. So instead the transaction itself is fully executed on the nodes, the transaction is crafted on the side of a so-called prover, but then it's a proof of its execution is submitted to Ethereum, and the proof is verified on all nodes. And then the storage is updated. So the proof just convinces all the nodes that the storage updated has progressed correctly. So the node themselves, they don't know what are the all steps that led to the storage update. They just check that the update was done correctly. So what's interesting about it is that, of course, the nice thing about it is that when a transaction is big, then it's, of course, better so that it's executed only on the prover side and the other just verify that it's correct. So the verification is faster than processing the transaction itself. The downside, of course, is that still the verification of a ZK proof is somewhat expensive. So we may hope that in the future we can aggregate these proofs, we can batch these proofs, we can do various optimization with those. But so far, well, as you correctly mentioned, so ZK rollups are still somewhat expensive. Another interesting downside, well, not a downside, but rather a feature of ZK programming is that the language that is used there, it operates on a bit different domain. So you may know that in usual programs, well, in Ethereum virtual machine or in Solidity, you operate with 256-bit numbers and you use 256-bit arithmetic, or on a regular x86 machine, you use like 32, 64-bit words, bytes, and so on. So they are all aligned to powers of 2. But in the ZK code usually uses a different domain. It's called a prime field. It's a set of numbers that are smaller than certain prime p. And as you get, and you can infer from the name, this prime is not a power of 2 because it doesn't factor into other numbers. And because of that, there can be all sorts of issues when you code in ZK. So we at ABDK, well, I'm DK in ABDK, and the other AB is my beloved wife, Anna. So we at ABDK with my longtime colleague Mikhail has audited a lot, really numerous projects that did ZK programming, and we have found quite a number of bugs. Well, most of these bugs are pretty subtle, so I will not go into details, but I will try to cover the most kind of simple ones, but still kind of informative enough for you to see what's the issue of ZK programming. So when you talk about ZK programming, we usually talk about so-called circuits. So circuits are not exactly the programs. So circuits, the feature of circuits is that they consist of so-called constraints, and these constraints are relations between the variables, or rather functions that are executed on those variables. So in regular coding, you just do instructions one after another. In the world of constraints, you impose relations on the data. And if you are familiar with, for example, database programming, working with the relations is way more different than working with real code. And with circuits, when we code in circuits, we have to satisfy two basic properties, which cryptographers call completeness and soundness. So, and they are like two sides of pretty much the same thing. So the understanding is that the circuits should behave exactly as the code. But what does it mean to behave exactly as the code? So on one side, the data, by completeness, we mean that every valid code should satisfy the constraints. But on the other hand, if constraints are valid, this means that the code must be valid. And this is called soundness. If you make a mistake in either side, there will be problems. So sometimes people say, well, completeness is not that big a problem because, well, in the worst case, maybe you can just regenerate your code. So the problem with completeness is you have some execution that is valid, you just cannot make a proof for it because of some bug in the circuit. But the thing is, of course, this may also lead to fund loss. For example, if what you are going to do is to withdraw some money from a rollup, for example, and if this transaction doesn't work, if it cannot be converted to a valid circuit because of a circuit bug, then you're screwed. So both may lead to funds loss, of course. And let's see some concrete examples. Well, not about the fund loss, but let's see concrete examples of bugs. What bugs are there? So the interesting thing about problems in the code and in the circuit is that when there is a bug in the code, is usually when someone exploits this bug, it's noticeable. You can usually, so the traces of exploit are stored, in particular when you submit, when it's in the blockchain, that everything is in the clear text. So a person submits a transaction, you see who calls which contract, you see all the commands, you can see the entire stack of code execution, and everything is clear and it's very noticeable after the exploit, after the code was exploited. The situation in the circuit is different. The difference is that since only a proof is validated on the nodes, the transaction itself is not validated. And because of that, if there is a bug and an adversary is able to create a proof, a valid proof for an invalid input, this means that the proof will be seen as valid. Everyone sees that the proof is valid. But the input is not known. The proof just asserts there is some input that satisfies the circuit. But if the circuit is wrong, you just don't see this input itself. Well, for data availability purpose, we often require that the data is provided so that the transaction should be reconstructed. But in general, if the proof is valid, you don't see what happens inside. And because of that, it might be very difficult to trace. If there is a subtle bug in cryptography or a bug in code in circuit programming, you may not see exactly how it was exploited. You just see, well, there is a valid proof, and then all funds are lost. So you must be very, very careful when programming circuits. So let's see some small examples, what I mean when I talk about constraints. Suppose that I execute a code where I compute a square root of x, so y is the square root of x. Assume that x is a perfect square, so we don't have any irrationality here. So suppose that y is integer here, and then in the circuit we program that y and x are linked by some relation. What relation is that? The relation is that y is a square root of x. It's the same as y square is x. Is it the same? Well, it's almost the same, because we want to exclude ambiguity here. The ambiguity is that if you tolerate negative numbers, then you should make sure that, for example, y is bigger than 0. Well, I already have strictly bigger than 0, but if x is allowed to be 0, then y can be 0 as well. And constraint here is that y square equals x, and y is bigger than 0. So far, so good. So for this sort of arithmetic operations, writing constraints is not that difficult. Well, ensuring that y is non-negative, somewhat difficult, but we can omit that. So assume that you can do this range check. So this is a simple constraint. But let's go into some more interesting examples here. So before we go into examples, I explain why it's a problem that you work on a different domain. So in ZK programming, and when you talk about things like ZK snark, we operate on so-called prime fields. This means that all operations are done modulo P. This P is typically for snarks, is close to 2 to the 256, but it's not at all 2 to the 56. Because of that, when you do operations where the result or intermediate variables get close to this barrier, to 2 to the 56, you may get problems. And these problems are exactly here. So you see, for example, when you have like two variables, x and y, and so that they are multiple overflows to the 56, then in plain EVM, you just get modular reduction. In Solidity, starting with safe math check, you'll get a panic. But in ZK snark, what you have is completely different. You don't get panic, you don't get modular reduction. Well, you do get modular reduction, but this reduction is modulo different number. So you multiply 4 by this 2 to the 54 plus 1. What you get is 2 to the 56 plus 4, but this modulo P. Well, this P is known, it's a constant, but it's not at all 2 to the 56. So the result is some weird number, possibly 250 something bit long. And as you can see from this example, you have to take care of this so-called edge cases. So whenever your arithmetic may approach 256 bits, you have to somehow constrain it. So basically, you have to prove that overflow doesn't happen in your case, because if it happens, it's very difficult to recover. So let's see which problems it brings us. And let's consider the second example. The second example is modular reduction. Suppose I want to prove, so I execute in the code A modulo B. Well, A and B are just valid numbers, valid integers, they're both bigger than 0, and R is the remainder. So is it okay if I program my circuit and I write this constraint that A is just Q times B plus R? This is the definition of modular reduction, right? So is it enough? A equals Q times B plus R. Well, clearly it's not enough. You should probably introduce R smaller than B. Then it's almost enough, is it? It would be enough if we worked in integers, but we work in modulo P. What happens modulo P? In the world modulo P, everything that may overflow will overflow. So how it looks exactly here. The thing is, adversary who want to submit invalid data and get a valid proof, adversary may be able to select both Q and R maliciously. The Q, you don't even care here. You think, okay, what's the problem with Q? I ignore Q, I only care about R. But the thing is, you do have to care about Q. Why is that? The thing is, in the field, any number can be divided by any other non-zero number. The division is always producing a valid operation and a valid output in the field. And the thing is, if adversary wants to get certain R as an answer, for any R smaller than B, bigger than B, there exists a Q that leads an adversary to this result. So if you simply give this as a constraint, what adversary gets, what adversary selects, he selects Q equal to A minus R divided by B. And this division always works. In the field, everything is divisible by anything non-zero. And if you substitute a minus r over b to the constraint, you see that the desired r will be the output. So if an adversary is able to select both q and r, then you're screwed. I will later see how we get around this problem, but this get around is rather complicated. So let me maybe outline several sources of bugs, several kind of most error-prone scenarios when we have this or similar problems. So whenever we have arithmetic that goes over the entire domain, so if you work with numbers, then that with multiplication approach to 56 bits or close, then there might be a problem because you have to range check almost every operation in your arithmetic. Whenever you have divisions, you see you have a problem because division in integers works differently from division in fields. You have to take care of that, you have to always keep in your head that everything is divisible by anything and the result may explode. For example, in a field, you can divide 2 by 3 and the result will be just a huge number. Whenever you have branching in your code, it's usually non-trivial in the circuit to implement it because you have to compute all of the so-called flags and you have to make sure that only one part of the circuit is executed or taken into account depending on the flag value. And of course, whenever you have so-called invariants and you have to work with relations among the data rather than direct functions with the data, then you also have problems. Let's see if, no, I don't have this update. Okay, so these were the most popular things. The less popular things are, I just listed here, so if you want to program some kind of finite automaton, like in zk-sync and its relatives, if you do range checks, then sometimes you may have problems. If you work with different flags, like if A, B, C, and D happens, but E and F don't happen, do this. And at the same time, if B and D happens, but E doesn't happen, then do that, and so on. So all this sort of exploitable. All the edge cases that in normal code are never executed will be exploited because an adversary can select all the variables that are part of a circuit that are not enforced from outside, and usually an adversary can exploit these edge cases. So these edge cases that can't be reached in a normal code will be reached by an adversary. So you have to double care about those. And of course, whenever you have some implementation of cryptography in your circuit, it's also error prone because usually cryptographic schemes have very strict restrictions on how they are used and with which parameters, and because of that, it's easy to misuse those. So, getting back to modular reduction, let me see if I do have modular reduction here. No, not exactly. So with square roots, actually, the problem with the square root also here, the so-called geometric mean bug. When you have two numbers, both of those smaller than 256 bits, and you want to compute their geometric mean. The problem is that the multiplication may overflow, and it's not even obvious how you deal with this overflow, because both A and B are valid inputs. So you can easily program the second part, that x squared equals to z, but dealing with overflow is non-trivial. What you have to do, you have to partition the number into kind of chunks and do kind of school book multiplication and deal with those. So you see how it's done here. You can you split actually not into two chunks but into three chunks. because when you multiply these guys, you have to ensure that they will not overflow themselves. You have to switch the representation for A, for B, for X. You have to multiply all these guys. You have to check the equations for different terms. And only after that, you can make sure that this geometric mean is computed correctly. Pretty much the same thing happens for modular reduction, for a long multiplication, and so on and so forth. So I think I'm running out of time, and I will not go into branching bugs, but those who are interested may go into our audit database, where we have a number of audits for various zero-knowledge projects and circuits, and see what kind of critical and not so critical but also dangerous bugs we have uncovered. Thank you.